Hello, and thank you very much for the chance to talk to you today. This is very much a talk appropriate for May 2021. I'm talking to you here from our spare room, and you're watching this from, wherever you are. Some of you are joining us on 27th of May, and others, of course, are watching this at some point in the future, and I very much wonder how these ideas will seem to you then. I'm going to start by introducing myself and then talking a little bit about my research interests, and then, of course, this is going to be about mathematics and Covid-19. So, my day jobs are that I'm Professor of Mathematical Biology at DAMT at University of Cambridge. DAMT is the Department of Applied Maths and Theoretical Physics. And here you can see the Centre for Mathematical Sciences on a beautiful day. And I'm also a Fellow of Queen's College. I'm the David N. Moore Fellow in Mathematics, and there's a nice springtime shot of Queen's with our bridge. And in terms of research, BC stands for Before COVID. These are my research areas. If you've ever heard me give a talk before COVID, either to general audience or a seminar to other academics, it will probably be one of these four areas. So firstly, I've had a long-standing interest in models for virus evolution, particularly influenza, of course. And my particular thing is models for co-circulating strains. So when you've got more than one variant circulating in a population and they're interacting through partial cross-immunity. There's some technical sides of that, how you make those models tractable within mathematics, and also, of course, interested in what that means for virus evolution. I'm very interested in spatial patterns as well as the evolutionary patterns. In particular, I've worked on a fair bit on the influenza pandemic of 2009, in particular looking at a US data set to try and understand retrospectively how that pandemic unfolded in 2009, and also how it's different to seasonal influenza. And of course I have a wider interest in how you build spatial models and how spatial transmission happens. I've been interested in also, related to the strains, but the virus bioinformatics, so using genetic sequences to try and pick out something interesting going on. That, again, particularly influenza. We've been looking at packaging signals to try and understand something about virion formation. And then, of course, the BBC pandemic, contagion. I'm not going to talk about this much beyond this slide, but this was a big citizen science project, and it was a TV show which was first aired in 2018. But the citizen science side of it was people volunteered to use the app, which collected data on how they moved during the course of a day and who else they mixed with. And all of this was building towards getting a stronger and better data set, a more recent one, of how people mix and move in the UK. And this was all building towards building better models ahead of some hypothetical pandemic, hopefully to happen a long, long time after 2018. But it wasn't to be. It was 2020. The BBC pandemic data has been hugely useful. I'm going to refer to one application of it in COVID-19. But broadly, where I am with this is my research interests are to use mathematics to understand infectious disease dynamics. And of course, I don't need to tell this audience the point of understanding infectious disease dynamics is to be able to help mitigate and control epidemics and pandemics. Well, that's all BC. COVID happens. So this is a plot along the top here from the government coronavirus dashboard of number of patients admitted by day to hospital. So this starts off, this is May, July, September. So actually just misses the start of the first wave here. And then you've got November, January, right up to where we are in late May. You've got the government's scientific pandemic influenza group on modelling, which is now better known as SPI-M, which I'm a member of, and SAGE, which is the Scientific Advisory Group for Emergencies, which I've participated in and contributed towards. And this is really where I'm going to be coming from in this talk. I mean, since February 2020, maybe January 2020, I've been very, very much involved in the UK's scientific response to this pandemic. I remain an independent university academic, and I really am only one of very many scientists offering our time and whatever our relevant expertise is in scientific advice towards the UK government through these bodies like SPI-M and SAGE. Let me emphasise today that I'm talking in my own capacity as an independent scientist, and any views that I express here are my own. A lot has happened in the science and in the policy advice, and today I also want to talk a little bit about the human side, the experience of being a mathematician working on Covid-19 during this crisis. Things for us have often been deeply challenging, and some days seem just beyond what is humanly possible. And of course, working on a pandemic during the pandemic has been absolutely horrifying. But among all of that, there has been bright moments, and some of them for me are as I've got to work with some really amazing people who seem to achieve the impossible on a regular basis. I've had a really privileged front row seat on the evolving science and the science advice. I've seen my own research fields change at an absolutely mind-blowing pace, and I actually feel really lucky to have had the honour of working at a time when it's our opportunity to step up to the mark and do our thing. This is, of course, as I speak, not something which is over in the past, but is all very, very, very much live. We are still in the thick of an ongoing global pandemic, and the conundrum for me with this lecture has been knowing what to include and what to not include. I've left the options open somewhat with the title of Maths versus Covid-19. But what I've decided to do is include the elements which I hope will be most interesting to this audience. And that means rather than one long mathematical or scientific topic, what we'll do is we'll hop around between ideas, between themes, and also along the timeline of the pandemic. But first, we'll explore the roles of modelling and what we can learn from classic results. So thinking about the role that mathematical modelling plays in fighting Covid-19, there's lots of different types of things it can do, and perhaps some of them are more obvious than others. I've got 4 bullet points of how I would think about it here. Probably the first 2 are more obvious than the second 2. The very first one is that modelling can be used for specific predictions. In other words, forecasting. So saying based on what we know about how Covid-19 and how transmission works, and what we know about where we are, what we think is going to happen in a few weeks, a few months, or longer scale time. So this is forecasting much as we'd understand it for weather forecasting, say. So these are predictions. Probably this has been the highest profile use of modelling, and perhaps is the most obvious one. Perhaps the next most obvious one is this one, exploratory work, thinking about scenarios. Now, scenarios are different to predictions in that they're still looking at the future, usually, but they're more saying, what if? For example there, so what if we were to close schools, what do we think will happen? What if instead we were to open schools, what do we think will happen? So then you can compare what the futures might be, at least according to models there. Again, that's probably one that you would think of, and in fact you're going to be familiar with seeing some of the roadmap modelling of predictions from different groups of what's going to happen if the different stages of roadmap modelling, unlocking in the future happens. These next 2 bullet points are maybe less obvious, but they're the ones I'm going to talk about. I think they're a little bit hidden in how they fit into scientific advice, but they are important. So the third bullet point there is understanding the drivers behind observed patterns, and I'll talk you through an example below, which I hope will illustrate what I mean by that. And then finally, mathematical modelling itself is a language, a really useful language on which we can build our understanding and human intuition of what's going on. And I hope we will go through that, and I'll help build your intuition in the next 2 slides after this one. Okay, but understanding drivers behind observed patterns first. You can see below there's a couple of different pictures, and this is actually extracted from a report that I presented to SPIEM quite early on 2nd of March 2020. It was using some insights from the spatial modelling for the UK, which was calibrated by the BBC Pandemic Project, and of course somewhat updated and adapted for our understanding of Covid-19 at the time. The model is a full spatial model, where the UK is treated as a lot of different separate patches. Probably can't see, but there's a gazillion little dots in here, particularly as you get to the more urban areas. There's a model of running what's happening within each town, and then there's the transmission between towns. There's age structure using the BBC mixing. There's short range and long range transmission. In fact, this model was totally overkill for what I'm using it for here. Now, what's different between the simulations I'm showing here is in this one on the left, we simulate introduction of Covid-19 to UK as a single event, right? Just happens once. And because of the narrative of the BBC programme, Hazelmere was the origin of the fictitious BBC pandemic, and I've used it for illustration for this slide here. I should emphasise we did actually try it starting from other places, but I like this one, so I'm showing you this one. So one initial seeding. On the right, instead, actually, there's many different initial introductions. In fact, there's 20 that happen over a short space of time. And this is to really illustrate how things would look different if there's like 1 or 2 initial seeding events versus if there's lots. And it's really, really strikingly different. You can probably just about see this is time, and the black curve is number of cases in UK over time. I wouldn't worry about the axes because it's just shifted so that 0's at the epidemic peak whenever it occurs in the simulation. The coloured curves you can see underneath are for the different regions in the UK. So, for example, South East is a region, Wales is a region, so splitting it up into 10 different sub-regions. And you can probably see here the coloured curves are fairly spread out. Some of them are a few weeks before others. Whereas on the right here, where there's lots of introductions, they're really much more in sync with each other. They sort of come up and peak around the same timing. In fact, more specifically, you can see with this one, you've got the first green curve there is London, which pops up 8 weeks before the peak of the UK as a whole. The UK peak is not straightforward because it's hitting different parts of the country, different times. Whereas here, actually it is London ahead still, but only by a week or 2. The colours in the map are which week that particular place peaks at, and what I hope you can see is there's a real spread of colours here on the left, but using the same colour scale, it's much more homogeneous here. Basically everywhere peaks at the same time, and that leads to a much spikier epidemic, much bigger peak, much more in sync between places. So the message of this paper was that with a few introductions, or 1 or 2, we expect heterogeneity in timing. There's a bit of chance in which region things arrive and how quickly they get to other regions. It's actually London that sparks first, even though Hazelmere is not in London. Epidemic upswing in some regions is going to be long before others. Whereas with many introductions, you expect synchrony and spikier epidemics. The trajectory is quite similar between different regions, only 1 or 2 weeks lag. And these really aren't scenarios or predictions, because you wouldn't just let this keep going. But this shows you what would happen, which tells you what you might start to see if we're in early March. If you're seeing regions all coming up together, which we were in early March, that's more likely indicative that there in fact were multiple introductions to the country. We weren't seeing things kicking off in some regions whilst literally nothing's going on in other regions. You're starting to get this pattern emerging of things happening the same in different parts of the country. So the observed patterns at the time were consistent with many introductions. The spoiler retrospectively is that we now have a clearer picture by using the genetics, so you can use sequence data to see the phylogenetic tree, the family tree of the viruses, to see that actually this first wave in the UK was seeded actually very, very many times internationally. So it wasn't just one spark, it sparked off lots of times in different parts of the country. So hopefully that starts to give you an idea what I mean by using the models to understand the drivers. This is not a prediction, it's not a scenario, but it's a way of saying, if this, it would look like this, if this, it would look like that. It looks like this one, so we can deduce there are multiple introductions. So that's the sort of not so obvious use of models that we can have there. And this was one actually done at the time. Okay. Stepping back then to more classic results, these are really, really valuable for having a language to talk about these things and for building a really robust insight. By robust, I mean if they're simpler models, they can be, while they're missing details, they are very generally applicable. They're not super special to some situation, so they will apply broadly, generally. What I'm going to show you here is using the classic SIR model, which I'm going to resist giving you 2 slides walking you through what the equations are, because I would expect many of you have seen this before. But using that to understand what would happen if, rather than having an unmitigated epidemic, we intervene to reduce transmission in some way, for example, by a lockdown. So what it does will depend on the strength of transmission reduction, i.e. how effective your lockdown or whatever intervention you have is, and also when the intervention is applied. Are you applying it very early or really only a long time after things have kicked off? We've got 2 plots here. On the left, you've got maximum cases, peak prevalence, and I've normalised it to be relative to an unmitigated epidemic. So proportion of original. So 1 means it's as bad as it would have been if you did nothing, and 0 means the peak is 0, nothing happened. And on the right, we have the total number of cases in the whole epidemic, which we know as final size. Again, 1 is the same as original, 0 is nothing happened. No cases happened. Then what we're doing is we're changing what the intervention is. The x-axis is the strength of the intervention. So transmission reduction is the same on the left and the right. It runs from 0 to 1. 1 means you've got some amazing intervention which magically stops all transmission completely. So it's like we've got a force field around every single one of us. 0 is your so-called transmission reducing intervention, does literally nothing. And everything sort of in between, so 50% transmission reduction, etc. What you can see with all the lines is the more transmission reduction, the smaller the total number of cases will be, and lower the peak prevalence is. So as you move to the right, the lines come down. Now, the different lines, there's some different coloured lines there, and these are when you intervene. Do you intervene when 0% of people have had this, after 5%, 10%, 15 or 20? So 0 is somehow you act actually before anything happens, and these are later. So to wait until 20% of people have already been infected is to wait probably too long, right? So this gives a range. And as you can see, the longer you wait, the higher these all are. So the higher the peak prevalence will be, and the higher the final size. So I hope the general ordering of things, that if you wait later it's not as good, if you have a higher transmission reduction it's better, just makes human sense. But you can do a little bit more with this. We'll get to that. But just to highlight again, oh no, I lied. I am going to show you the SAR equations. So you can actually reduce it to a two-dimensional system. S is the number of susceptibles, I is the number of infecteds, and mathematically you can just write it down like this if you scale out time, and then you've just got one parameter, which is the reproduction ratio, R. And I'll give you a reference for a paper walking through all the mathematics of this, but the absolute crux of the maths means you can actually write down all these results. It can be done by hand. Is that the SIR system has a constant of motion. This function of S and I, S plus I, minus log S over the reproduction ratio is constant under SIR dynamics. It's like energy in mechanics. You can use that it's constant to work out lots of things. So you can calculate peak prevalence. You can differentiate this with respect to S and find its peak. And final size. You can use initial and final conditions to find out what initial S is and final S, and the difference between them is the number of people infected. It's very satisfying maths and fully within reach of certainly a first-year undergraduate and probably a keen A-level student with a bit of help dealing with the two-dimensional system. Okay, what can we do beyond saying harder interventions reduce things or earlier interventions are better? Well, I think there's three key insights from this immediately. First is you need early interventions and strong interventions to stop things. If you want to be down here where the proportion of the original peak is small and final size is small, you've got to have pretty effective interventions that mitigate most of transmission. And you also want to be using the 0% curve or 5% curve. You want to intervene early. And again, this should be intuitive by now. You intervene early and you intervene hard if you want to stop an epidemic. But what happens if your only available intervention is weak, or the only one you're willing to put in place? Because these interventions we now understand are costly in very many human ways in their own rights. Well, if you've only got an intervention which, say, brings transmission down by 20%, what does it do? Well, you can see here, you can bring the peak down by, well, more than 20%. This is below 0.8. But the final size is actually not much reduced, less than 10% reduced. So weak interventions are proportionately better at bringing down the peak than the total amount. And this is very much the phrase that we heard a lot in spring 2020 of flatten the curve. That's what this means. A weak intervention will do this. Actually, an interesting thing also with the weak is the lines are very clustered at these points, right? So whether you apply your intervention early or late doesn't make a lot of difference, right? Unless you wait until ages after the epidemic or something. It's not very sensitive to timing, because essentially what it's doing is crushing the peak, not the early part of the epidemic. If, however, you've got a really strong intervention, and we now know the UK lockdown was a strong intervention, it was enough to turn transmission over and bring the epidemic down, then it becomes more important to apply it early. So say you're talking about something, the ballpark, it brings transmission down by 2/3 or 3/4, then you can see these lines are spread out very much. So if you intervene later, it's much less good than intervening early. That's peak prevalence, and same thing on final size. So if you are going to intervene hard and keep your measure in place for a long period of time, of course this one, the SIR simulations here, I'm assuming they stay in place forever. It's important to apply early. You can extend this analysis to look at what happens if you do interventions of a fixed duration. When is it optimal to apply them? And the other thing that we did do is look at the same analysis, but assuming you've got partial immunity, which was relevant for thinking about the second wave in the UK, when we knew there was at least some immunity among the population. Do these insights change very much? Actually, what I've shown you here, or at least the essence of it, is a paper to Sage, which I sent in February 2020, which was in there. I'd already learnt by that time that less is more, so sending a one-pager with key insights was worth it, but it has to be short. But I can assume the readers are intelligent people who can grasp it quickly, so I just go for one or two main points. There's lots of things I like about this, not least getting essentially results that are over 100 years old back onto our consciousness to think about, because they are relevant here. Also delighted to have simple models in capital letters in a file name of a Sage repository paper. But in seriousness, at the bottom of this I had this sentence here. This simple approach should not replace models including more details, but if predictions from more complex models deviate substantially from those shown here, the factors behind this difference should be identified. And in context, this was going to Sage at a time when far more intricate models were going with very specific predictions. And I'm saying the simple SIR is useful as a benchmark to give you an idea of what's going on. If the more detailed models are telling you something slightly different, it doesn't mean they're wrong. Maybe they're more likely to be right, but you can gain an insight by understanding what factor is it in that more complex model that means that it's different. Is it because they're thinking about the UK as heterogeneous? Is there something different in the assumptions about how COVID works? But what is it that makes it different? You can use these as part of a suite of approaches to help understand this. This work is written up with more discussion here, so the mathematics has walked through, these figures are in there, and there's actually more discussion about how these can be used in context with more complex models, and that was work with Deirdre Hollingsworth, and in fact, well, hopefully that's been published today, and this DOI link will work for you, and that's in Filtrans B. Now I'm going to go one step even more simple, and this is to the bullet point of using this as a language to build insights still. I realise that the audience watching this are very heterogeneous. Some of you are going to be undelighted that I've put up any form of equation, and because this is joint with LMS, some of you are maths professors and you're going to know all this stuff already. I claim this simple equation here of geometric growth gives insights for everyone still, even disease modelers, right? So yielding insights, building intuition, simple is good. Let me tell you about this. So Y is the number of cases after n infection generations. There's n. We've got a multiplicative constant out the front here, A, and capital R is the most famous parameter of 2020. It's the basic reproduction ratio, R. And it's simply R to the power of n, so number of secondary cases in the next generation, just multiply it by R from the previous generation, and you get this geometric growth. You can work this out even on your by hand, pocket calculator, generation 0. Starting condition, if I put A equals 1000, then Y of 0 equals 1000. After one generation, I've got 1200. After two generations, I've got 1440, and so on. You can either plot them as points or just join them up by plotting this with a continuous n, so it's fine. N is disease generation, which you can sort of think about as time, if you're happy to scale that to mean 4 or 5 or 6 days. It's not strictly accurate because disease generations end up overlapping quite quickly, because you can have someone infect someone quite rapidly, or it can be long generations, so the generations end up intertangled. But if you think about this as time, you still gain the intuitions that you need from this. Alright, so now let's suppose, rather than cases, this represents hospitalisations. So that could be if the true cases are, say, 50 times or 100 times or 10 times as much. And this constant A sort of now scales for what proportion end up in hospital. And we've got this curve. R is 1.2. We started with 1,000 this generation. What happens mathematically is the parameters change. And then what insight does that give us on hospitalisations? So in red, I'm going to boost the coefficient at the front by 50%. So rather than 1,000, we go to 1,500. And in blue, we're going to boost this ratio R by 50%. So rather than 1.2, we're going to 1.8. Now, if you're watching this not live, you can pause and just make sure, think through for yourself what these curves look like. Where are the red and the blue curves going to appear on this graph? This is something which totally doesn't work in the live lecture, but you could pause it. And I'm going to assume you're either not interested in pausing it or you've now finished pausing. Because a bit of a trick question, it just doesn't sit on this plot. In order to fit the blue and the red curves on, I've got to rescale my y-axis, so our original black curve is now down here, skirting along the bottom here. So what's going on? Well, the red curve, I'm just increasing A by 50%, and that just scales up Y by 50%. So the red curve is just the black curve, but with 50% extra. So it sort of looks like the black curve the whole way through, just scaled up a little bit. The blue curve is different. It starts in the same place as the black curve. In fact, it sits under the red curve to start with. But because this ratio is larger, it just grows a lot more each generation until rapidly it's a long, long way from the red curve and the black curve. So this boost to R after a few generations is a much, much, much bigger deal than a boost to A. All right, so if we think about trying to translate back to hospitalisations, well, this stage of thinking back is the modelling happening. To increase this coefficient at the front, that would be what you'd do if you were trying to say, okay, well, this coefficient was wrong. Actually, this disease is 50% more severe than we thought, i.e. your chances of being hospitalised are 50% higher. That red change is what you'd do. However, the blue is what you'd do if you say, okay, actually it's 50% more transmissible. I need to scale that R up by 50%. You go to this curve. And I hope that starts to build intuition. It's really all about the transmission. It's about the R. It's the ratio of cases. Severity sounds frightening. And of course it's, worse for someone who gets it. But the point is, fewer people get it, right? So if it's much more transmissible, you've got a lot more cases. So in short, when thinking about epidemic dynamics, it's transmission, and transmission that matters. We'll come back and use these ideas again, but I hope that's communicated that it's this increase in transmission that matters the most. This part of the lecture will be more narrative on what has been happening with the modelling and how we have worked together to assist with the government scientific advice. This, of course, is necessarily from my own point of view in terms of how I've seen events and what organisations I've been part of and in touch with. You've seen this slide already, but I want to think again about SPI-M. SPI-M existed, of course, before 2020, but as the pandemic loomed, it spun up, and in that I mean both many more meetings and many, many more researchers and subgroups, and it just expanded. SPI-M pulled in wider epidemic modelling expertise, really in light of what the needs of this pandemic was. SPI-M fundamentally works by combining insights from different models, but also from different modellers. We routinely work under very intense time pressures, and we often work on questions which are essentially not really answerable. the cycle of how intensely busy we are has unfolded in some sense with the epidemic, but somehow we never really had a quiet period. We've been on the go absolutely solidly, and we still are very much busy with things. Thinking about the wider math and physics community, I want to talk briefly about this article, which has a little bit of a story to it. One of the editors from NatRefPhys was in touch with me and was after an opinion piece, but somehow it caught me in early March, at a time when I very much felt the need to share an opinion. I think she asked for 200 words, but got somewhat more, and not even about the topic that was asked about. And thinking about it, I don't even think it was on time either. I actually wrote the first draft one evening in March. This was before lockdown, but when the looming pandemic was very, very much on everyone's minds. A lot of colleagues, not so much the disease modellers, but colleagues in maths and related quantitative sciences, were writing to me, and in some sense this first draft was a reaction to that. I have to be honest, the first draft I wrote was essentially a rant, and it was a rant about things that it would not help for the wider community to do. But this is an absolutely marvellous editor who saw that there was a possibility of a much more positive article in there, and we back and forthed it between us and came up with the article as you'd see now, actually. But there is some of the original snark which survives in the second paragraph there. A brief summary of it. Remember, this is for the research community, but not specialist epidemic modellers. There was a role for them to play in amplifying the signal, not the noise. And in research worlds, that means things like, the preprint servers were absolutely rammed with papers appearing every day. But picking out what of those actually contained useful information or useful insights and passing them around, that was important, or even giving short summaries of them. Communication to the public was very important. We needed those who really understood how models and epidemics work to dispel misinformation and comment also very much at that time on what models can and can't do. There wasn't much public understanding there of that. And finally, on contributing to research, the wider field, starting from scratch wasn't going to work in the midst of a pandemic. So instead, the alternative was to join up with larger efforts and start from the state of art, find ways to join in with other things going on. And RAMP, which I'm not going to talk about in great detail here, but rapid assistance in modelling the pandemic. This was a scheme convened by the Royal Society and chaired by Mike Cates. And RAMP was sort of very much part of this world, bringing the wider community into Covid-19 pandemic response. I think there is much more to be said about how modelling and mathematics and related fields joined up, what we did get right and what we did not get right in terms of how we respond to scientific emergencies. Much of it was very specific to Covid-19 in early 2020, but I think there are lessons to be learnt for how science responds to emergencies in the future. So, JUNIPER. JUNIPER stands for Joint Universities Pandemic and Epidemiological Research. I've already mentioned that SPI-M brings together research from many different research groups. Some of those groups are already basically in large multi-group modelling squads, in effect, through their home institutions. I'm thinking of Imperial College and London School of Hygiene and Tropical Medicine. But most of the rest of us were smaller research groups. But we had many interlinks between us. For example, we overlapped earlier in career or had the same PhD supervisor. So this consortium emerged really rather naturally. I would say we were basically functioning as an informal group in mid-2020, but we were formally funded by UKRI in November 2020 and we're ongoing now. Here's the 16 of us who are principal investigators or co-investigators. And there are really, really many more people who are not pictured on this, the postdocs and others who are part of Juniper. Our senior scientific programme manager, Dr Kira Dangerfield, is not pictured, but she's really key in terms of how we work together. I'm going to come back and talk about the science writing in the next slide. But if you want to know more about us and what we've been up to more recently, please do have a look at our website. You can sign up for our newsletter, there's talks online, or follow our Twitter, of course. We're very closely linked with the Newton Institute, and again, this is about interfacing with the broader academic community, so to sort of connect outwards from our somewhat SPI-M-based core and what we're doing at the moment, thinking about longer term and thinking about wider problems. And the Newton and communicating through the Newton is very important for that. So we've done a slightly unusual thing in Juniper, as in I haven't seen this happen in any other large scientific consortium, but we have in-house science communication expertise. Marianne Freiberger and Rachel Thomas, pictured here, are the editors of PLUS magazine, and they're working very closely with us in Juniper. Indeed, they're part of Juniper, which means rather than hearing about stuff a long time afterwards the research is finished, they're in our key meetings and talks, and they're knowing what we're up to, which means they can pull this together for public communication very quickly. So PLUS magazine, and there's a snapshot of the website, is for a broad audience, which includes school students, it's for public, it's for media communications, and there's also something which we come to term explainers. For example, every Friday you'll get the update, or every Friday at the moment at least, you get the update of what SPI-M consensus R value is and the growth rate for the UK. Buried in there is a comment on how to interpret a growth rate, and you'll see further technical information on growth rate can be found on PLUS magazine, and it links back to this explainer written by Marianne and Rachel. So that's there every week. Finally, to skim around some of the topics I've been involved with Juniper and SPI-M, and I should emphasise I'm one researcher among many working on all of these things. And I can't even talk through all of them, but some of the key ones perhaps. Schools, I've been very interested in what's going on with schools and children in this pandemic, of course, both in terms of the pandemic and also mitigating the harms from school closures. And related to that is higher education in universities. Working on universities, we've had a group centred through Juniper and the Isaac Newton Institute, and there I've been working week to week with one of Gresham's previous professors of geometry, the marvellous Chris Budd. Definitely goes under the list of delightful things that's happened in this, but I've got to work with some amazing people, and the HE group are very much part of that. Variants, of course, in December B117 and live now B1617.2. They are dreadful names, aren't they? And really, basically any of these could be another 1 hour lecture in its own right. But don't worry, I'm only going to talk about one more now. Turning now to the last part of this lecture, we're going to have a think about vaccination. This cartoon really helps me. So focus on this person here. Without vaccination, this person is fully susceptible to infection, so can be infected by other people, can infect other people, so contributes transmission to others, and has a chance of a severe disease outcome, which you can think of as hospitalisations or deaths. Potentially, vaccination can modify all three of those things. So vaccination can reduce the chance someone even becomes a case, whether mild or severe. Even if they are a case, it can reduce the chance they infect others. and if they are a case, it can reduce the chance of severe disease. So all three effects are actually in there. And we can think of this as susceptibility reduction, transmission reduction, and disease reduction. But really, it's the combined route of disease blocking, so getting infected and chance of severe disease, so it's sort of these two multiplied together effects, and transmission blocking, the chance that someone gets infected and infects others. So there's really sort of two main effects of vaccination: blocking disease and blocking transmission. Now, we can translate this back immediately using the insights we had from earlier. So remember this again. We've got A r to the n. If I plot this is again A equals 1,000, R equals 1.2. We've got the black curve again. If vaccination has the effect of reducing the chance of disease by 50%, that would be like reducing this coefficient A by 50%, so the whole curve would just drop by a factor of 2. If, on the other hand, vaccination reduced transmission, it was transmission blocking by 50%, this would be to reduce R by 50%, and this is a much bigger deal. So it takes it from this black curve down to this blue curve. So once again, anything you can do to disrupt infection, once you go more than a few generations of disease out, i.e. a week or two, anything transmission blocking is far more important on the longer term. And really, that underpins what happens next. This insight will explain this next bit. So I'm going to ask a harder question for which there's no simple answer. And I'm not even going to fully answer it, I'm just going to give some pointers towards ideas. Vaccination rollout. Who should we be targeting with vaccination? Of course, this is what actually happened in the UK. Through November, December, vaccination rollout starts in December, and it's very much in the context of a live wave and turning over that wave. The difficult question I'm going to ask, even though it's already happened, looking back, or thinking about a future pandemic or another country, how do we decide what vaccine priority order should be? And here's some points here. What should the priority order be? Should it be the most vulnerable, the people who have the highest chance of severe disease? Should it be perhaps those who are most put at risk by the work that they do? For example, healthcare workers. Should it be those who are most needed at work, which of course includes healthcare workers, but you can think through other roles where if they were out of action it would be societally very disruptive? Or should we be targeting vaccine to get those who are most connected with other people? And you might think you know what I'm going to say on this, having thought about the previous talk, and I say transmission is everything. But actually this is really subtle. It really depends what you're trying to achieve here. And there are hard human decisions to be made. There's complex ethical issues here for society. Mathematical modelling can't answer those ethical issues directly. There's a human decision to be made. But where we fit is mathematical modelling can show what the population level consequences of these different options would be. And I should emphasise here, I'm not criticising at all what the UK did. I'm sure it was right. But I think it's also fine to go back and think about what else we could do if we knew we had a different type of vaccine or a different situation in future. So here's a simple approach here. So it really comes down to population heterogeneity as to who you're going to choose to vaccinate. And you can think of the whole spectrum of society being complex, or you can just take it down to two simple groups. So I'm going to split the population into two. There's going to be the vulnerable. You might think about this as the older part of the population, who have a higher probability of severe disease. And the mixers, who do a lot more interacting with each other and other people and the vulnerable. They're just much more mixy, but they're not so vulnerable to disease. and split the population 50-50 just for initial exploration. And as this is a joint LMS Gresham lecture, I'm going to lapse a little bit into maths, but I'll tell you what this means in a bit. But just on these slides here, we've got a mixing matrix here. So the mixers mix m times more with anyone. What I mean by that is the columns are those who are doing the infecting, vulnerable mixers, and the rows are who they infect, so the vulnerable mixers. If I normalise it so the vulnerable to vulnerable is rate 1, then vulnerable to mixers is rate m, because the mixers mix m times as much. Mixers to vulnerable is m, and mixers to mixers is m squared. And that's what I mean about this with anyone. There's no preference for mixers to mix more with mixers. That sounds terrible as a sentence. There's no preference of who's mixing with who, it's just how mixy you are, full stop, and it gives you this matrix structure. I hope you can make sense of that. There's more of this in this preprint here, which is actually about vaccine escape as well as about vaccine strategies. Now, vaccination. So we take this situation and we can go ahead and do some vaccination. So we vaccinate proportion V1 of the vulnerable and some proportion V2 of the mixers. Now effectively we've got 4 populations rather than just 2. The unvaccinated vulnerable mixers and the vaccinated vulnerable mixers. And this now gives us a 4x4 mixing matrix, which looks a bit yuck to start with, but actually there's loads of structure there. Each of the 2x2 blocks is essentially started by the 1m squared matrices from before of the mixing. The rows have these multipliers of what proportion of the population is in these groups now. So 1 minus V1, 1 minus V1, 1 minus V2, V1, V2. And these thetas are these modifiers because of vaccination. So these vaccinated vulnerable and mixers are less infectious. These vaccinated vulnerable and mixers are less susceptible, and it gives you this structure. But the nice thing mathematically is, even though this is a mess, you could build this out of, if you multiply all the rows by this and all the columns by this, you get this matrix. So it's got the structure of being an outer product. The nice thing there is that if a matrix can be written as an outer product, then, if we're interested in its eigenvalues, all bar 1 are 0, and the one that's non-zero is actually just, it's the trace, which is the dot product of these 2 vectors here. This is really good because if you've got a next generation matrix, the effective R that we get from it is proportional to the dominant eigenvalue, the one with the largest modulus, which is always real and positive because everything's real and positive inside the matrix. So we can write down a nice expression for how R scales as we change from no vaccination, when it's R0, increasing vaccination. And it's literally this, which you can probably see greatly pleases me that I can just write down a pen and paper result. It's not just for mathematical entertainment. The strength of this is it is an analytic result. You don't need to check my code. The result is there. It's not tied up in computation. You can take that and you've got an R value and you can go ahead and say, okay, so I'm going to run an epidemic forward for a few generations, which we can also do analytically, and say how much disease there's going to be if I vaccinate a certain number of vulnerable and a certain number of the mixers. So on the horizontal axis here, I've got what proportion of the vulnerable I'm vaccinating, and on the vertical, what proportion of the mixers. So bottom left is no one is vaccinated, top right is everyone is. Out here on the horizontal, I've vaccinated the vulnerable but not the mixers, and vice versa up here. The colours I'm plotting are how much disease there is relative to an unmitigated situation. So down here in this corner here would be if no one's vaccinated, it's 1, it's normalised to that. And as you vaccinate people, it drops off. So it's highest here and it drops down. It actually drops down to effectively 0 pretty quick, because I'm assuming there are other interventions in place as well. So some partial lockdown, for example. Now, what can you tell from this? Well, it's really about the direction of these lines. Suppose I've got enough vaccine to vaccinate 40% of the vulnerable, or 40% of the mixers. Which one's better? First instinct might be it's the vulnerable, because you're trying to stop disease, and they're the ones who are going to get it badly if they get it. But actually that's not true. You get down to lower numbers, you drop down the contours faster if you go up vertically here to vaccinate the mixers. And the intuition behind this is exactly as I've shown before with those geometric growth. It's getting the transmission down just reduces the cases in the vulnerable. So even though the vulnerable may not be directly protected, the indirect effects accumulate much faster of getting transmission down. So if vaccination has some transmission blocking effects, then it can be better to use the vaccination to reduce transmission rather than directly protecting the vulnerable. I'm going to caveat this quite carefully here. There's many caveats, and please do have a look at our paper on this. There's in fact a page and a half just called caveats. This is really dependent on timescales. Actually, you saw in those exponentials a few slides ago, actually they cross over after 1 or 2 generations. But if you're thinking about a very short-term intervention, like you've got an explosive situation and you just want to deal with it, with what's going to happen for the next few weeks, then on the very short term, it's more intuitive to vaccinate the vulnerable, and that holds true. All of this work was limited by thinking about 2 populations only. And really, reality is a real spectrum of mixers and vulnerable. You can think about it in terms of ages, so maybe the older are more vulnerable for severe outcomes of disease. Certain age groups, younger adults are more mixy, but you've also got different vulnerabilities within different age groups. You've got some young adults who've been shielding through this pandemic, and you've got different mixing, and then, as mentioned before, you've got complex interplays like healthcare workers. They're both sort of part of vulnerable and mixing, in that they could infect vulnerable and they're part of the nodes of mixing. So really, caution here, this is only a 2 population model, but it does at least give an insight which makes some human sense. But if you go ahead with intuition and combine these, you can see that an optimal strategy, if you're dealing with the vaccine rollout, just to bring an outbreak down, optimal strategy under realistic conditions could be to vaccinate the extremely vulnerable first, and then pivot to tackle the most mixing if you've not been able to get cases down by other means. It will really depend on the precise population distribution, and I should caveat that this is less important if you found some way of getting cases down by other interventions. But this is where the talk comes to a stop quite abruptly. There's ongoing work here. This, as mentioned right at the start, this is the talk which is happening sort of whilst we're still live working on this pandemic. Indeed, tomorrow morning I'll be back in meetings with the Junipers to find out the latest work on new variant. So that's where I'm going to end it. Please have a look at some of the papers I've linked, and some of the sources of finding out more of what we're up to at the moment. I know this has been a bit of a whistle-stop tour through different topics, but I hope very much this has given you some insights into how modelling has fitted into scientific response to Covid-19, and how maths versus Covid-19 is working. I hope this has been interesting for you. Thank you.